This is the last section of the book on power series, and it's a nice wrap-up. We're kind of finished with theorems on power series, and this is a nice application that takes us back to differential calculus. We're going to see how you can use power series to solve initial value problems. Initial value problem, you've got a differential equation and you've got possibly some initial data. And you want to know that there is a solution and you'd like to find it. Well, what we're going to be able to do with power series is produce solutions. We won't technically know that they're unique. Well, actually, our method of solution will tell us if there's a power series solution. The one we found is the unique one. But at least it's conceivable theoretically that there are other solutions that are not power series. We're not going to go into that theory. The point of this is to give an example of how to apply what we know about power series as functions. In the examples I'm going to give, we're going to get a power series for a solution, and we'll also be able to write our solution in a closed form. We'll say, this power series is this one for e to the x or this one for cosine. But in general, you shouldn't expect that from power series solutions. You'll get some coefficients, or you'll get some iterative equations, we'll see what that means, that tell you the coefficients in the power series, but maybe the power series isn't anything you recognize, or if it's recognizable, it's not easily recognizable. And that doesn't matter in a lot of applications because power series solutions, you can use the first few terms to approximate well near the center. And so in applications, if you just want to approximate fairly well, you just take the first few terms of your power series solution. Where are the power series centered? Well, if you've got initial data, then you would want to center your power series at the x-coordinate at which you've specified the initial data. If you're not given any initial data, you just have a differential equation, then either you need to know ahead of time for your application what x values you're most interested in, then you'd want to center near there, or just pick a convenient center when the most convenient one is x equals 0. So let's do some examples. Let's solve. Let's do one that we can do by hand first. Let's solve dy dx equals x times y, and y at 0 equals 5. Okay. So we'd like to solve this differential equation using power series. Well, first of all, we're going to solve it without power series, see what we get, and then see that the power series solution gives us the same thing, though it may be, it helps to know ahead of time what it's supposed to equal, and then we'll look at our solution and go, aha, yes, that's what it is. So this is separable. You should remember that it's separable from differential calculus. You divide both sides by y and multiply by dx. If you wonder why it's okay to multiply and divide by or divide by these individual differentials, try to remember it's just kind of suggestive notation. And while it doesn't mean anything really technically right here, as soon as we integrate, put in the integral signs, it does. So divide both sides by y, multiply by dx, and you integrate both sides. And over here, we don't have to worry about y being identically equal to 0 because our initial y value is 5. In fact, we'll go ahead and assume y has to be positive, since typically you only expect solutions to differential equations to hold near the initial data. So assuming that y is always positive, since it starts out at 5, it's fine. It's at least positive everywhere near 5. Integrate this. Normally you'd get the natural log of the absolute value of y, but we're assuming y is positive, so we'll just get the natural log of y equals x squared over 2 plus a constant. We'd like to solve for y. You raise e to both sides, and you get y is e to the x squared over 2 plus c. You split off the e to the c part, and that's just some new constant. So you get y equals a e to the x squared over 2. Maybe a long time since you solved separable equations, but that's what you do. Now you plug in your initial data that when x is 0, y is 5. And you get 5 equals a e to the 0. E to the 0 is 1, so you get a is 5. And then we have our nice closed form of the solution, the unique solution to that initial value problem, y equals 5 e to the x squared over 2. I'm going to leave that in this corner because now we want to see how you do this with power series. Not because this is not to apply to a problem that we can easily separate, like this one. Right? Of course, this is how you would solve this problem. But you can find power series solutions even for non-separable equations, for equations for which no one knows how to solve them in a nice closed form. Closed, finite, as an elementary function, some finite combination of our standard functions. And yet, power series solutions can be fairly easy to produce. So let's see how you approach this with power series. So first of all, where do we want to center our power series solution? We want to center it at this x value where we're given the initial data, so at x equals 0. So we're going to use a power series centered at 0. You can think Maclaurin series, but typically when you say Maclaurin series, you mean you have some function first, and then it's Maclaurin series. We don't have some kind of predefined function, but if you want to call it a Maclaurin series, I won't complain. We're going to look for a solution like this, that's some infinite series centered at 0. So, and the whole point is that the power series is completely determined by its coefficients. And so we'd like to see what these coefficients are. So, what do? Let me also get the differential equation, or the whole initial value problem, out of my way. Let me put it here. dy dx equals x times y. Y at 0 is 5. Well, we know how to differentiate power series. You differentiate like they're infinite polynomials that never end. We know how to multiply x times a power series. So we know how to calculate this side in terms of power series. We know how to calculate that side in terms of power series. We know that power series representations of functions are unique when you specify a center, if they're both centered at 0. Then you match coefficients on both sides, and you get conditions that all the coefficients b have to satisfy. And then you solve those conditions. So let's see what we get. Certainly the initial condition is easy to deal with. We want y at 0 to be 5. So 5 should be y of 0. On the other hand, if you plug 0 in here, all these terms go away, and you get b naught. So we immediately know that in our power series solution, we're going to have b naught equals 5. Okay. Phew, that was tough. But now we want to differentiate. So what do you get when you, right? We want to require this to be true, that dy dx equals x times y. So what is dy dx? It is, you differentiate this, the derivative of a sum is the sum of the derivatives, so you can just write this. You need to start at the constant term b naught, its derivative will go away, and you'll start with the degree 1 term, so the first power of x. So I'm just going to start at k equals 1. And then you can differentiate this to term in time. bk is a constant. The derivative of x to the k is k, x to the k minus 1. And you could write out some terms of this. It means we've got b1 plus 2 b2 x plus 3 b3 x squared, and so on. I guess when I wrote it like that, I put the k here and the bk over there. So to make it match that, I could write that. It's going to be helpful for us to re-index this. So to call k minus 1 something so that x, I'll call it j, so that we have just x to the j, and also so that this will start at 0. That will turn out to be helpful. It doesn't matter what you call the index, so after we call it j and kind of rearrange the summation, or write it in a different way, it's true we could go back after that and replace all the j's with k's, but I won't. I'm going to let j equal k minus 1. And if you add 1 to both sides, that means k is j plus 1. So that this summation for dy dx, we'll have dy dx equals the sum. I want to rewrite things in terms of j. So when k is 1, j is 0. So j starts at 0. And of course, as k goes to infinity, j goes to infinity. That's not an issue. K becomes j plus 1. K becomes j plus 1. But the reason we did this is so that, or one of the reasons, is so that x to the k minus 1 is just x to the j. Now, don't let this reindexing confuse you. This is something you do when you write this in summation notation. As far as this goes, it'll look exactly the same. You plug in j equals 0. What do you get? You get 1 times b sub 1. So you get 1 times b sub 1 times x to the 0. So that's times another 1. Plus, what do you get when j is 1? You get 2 b sub 2 x plus. It's exactly the same thing. We've just written it in terms of a different summing index so that we can do something nice in a minute. All right, so here's what we get for the derivative written in summation notation. All right, now we've got y is the sum as k goes from 0 to infinity of bk x to the k. And on the other side of our differential equation, what we really had was x times y. So what's x times y? Well, you just multiply this by x. That multiplication by x distributes over the summation. So you get the sum as k goes from 0 to infinity of bk x to the k plus 1. But we'd like for this to match our earlier summations indexing. We'd like an x to the j up here. So here, we let j, just to reindex this summation, we let j be k plus 1, so that k is j minus 1. Okay, so what do we get? Well now, so x times y then is the sum. We're going to write everything in terms of j. K starts at 0, so j starts at 1. And as k goes to infinity, j goes to infinity. B sub k is b sub j minus 1. X to the k plus 1 is j. And so we get this. Again, don't let this confuse you. When j is 1, this means you get b sub 0 times x to the 1. And then when j is 2, you get b sub 1 x squared plus, all we've done is multiply our original series by x. Okay, so where are we right now? We have just found that our differential equation, that dy dx equals x times y, so we started with y equals, the sum is k goes from 0 to infinity of bk x to the k. We've just found then that the equation dy dx equals x times y becomes the sum as j goes from 0 to infinity of j plus 1 times b sub j plus 1 times x to the j, so that was this, dy dx, equals the sum as j goes from 1 to infinity of b sub j minus 1 times x to the j. This. What do you do with that? This certainly looks worse than the separable equation, but it's really not. what do you do with this? Power series representations are unique. The coefficients of the various powers of x here have to match. And the reason we re-indexed with just have x to the j is so it's easier to do this matching instead of we had a k plus 1 and a k minus 1. But now they have the same indexing so that the term in front of, the coefficient in front of x to the j on this side has to equal the coefficient in front of x to the j on the other side for all j. Now, you should notice something immediately. This one has a term, this one starts at j equals 1, this one starts at j equals 0. So this one has a coefficient in front of x to the 0. This one doesn't even have an x to the 0 term. But think of it as it's 0 times an x to the 0 term. In other words, this one has no constant term. But that has to match what's over here. So the point is the coefficient in front of the constant term on this side has to be 0, right? Because this side has a constant term, this side either doesn't have a constant term or its constant term is 0, which is a better way to think of it, which means when j is 0, we would get 1 times b sub 1 as the coefficient. This has to be 0 because that's the constant term over here, what you get when j is 0, 1 times b sub 1, and the constant term over here is 0. So we have to have this. Aside from that, for all j greater than or equal to 1, so what do we get after that? For all j greater than or equal to 1, the coefficient over here has to match the coefficient over here. So we have to have j plus 1 times b sub j plus 1 has to equal b sub j minus 1. All right? Or thinking of, we've got the early coefficients first and you want to know about the later ones, you could write this as the jth plus first coefficient is j minus first coefficient divided by j plus 1. This is an iterative formula for the coefficients. It tells you that you want to know a higher coefficient, a higher b sub j plus 1, you need to know a lower one. Sometimes you can get nice closed formulas for the coefficients from this. Sometimes it's not so easy. Keep in mind we know that b sub 0 is 5, and we also know that b sub 1 is 0. All right, and what we hope is that from knowing these two kind of starting b values and having this iterative formula, this is for j, I'll write it again, this is for j greater than or equal to 1, that tells us what all of the b's are. And they do. And once we have all the b's, that tells us the power series. And so it gives us a solution. Really, technically, we should check the radius of convergence of our solution to make sure we have a solution that exists for some x's beyond the center. But we're going to see, in fact, that our solution agrees with this. And so we'll know that it's true. So we start with, now our problem is this. You've got b naught equals 5, b1 equals 0, and for j greater than or equal to 1, b sub j plus 1 equals b sub j minus 1 over j plus 1. Now, technically, at some point here, we should do something called induction. You should prove that some formula is true by induction. But in fact, you don't want to get too carried away with inductive proofs, and what we'll see will be completely convincing even without it. And in a lot of cases, I'll say it again, you shouldn't expect nice closed formulas or that they're easy to find. And so you would just write the first few b's and then use the corresponding partial sum from the infinite series to approximate the solution that you're looking for. But, in fact, we'll be able to do better than that. So what happens here? This, because this is b sub j minus 1 and b sub j plus 1, you skip terms here. This tells you you need to know what happens 2 before this one to know about this one, not 1 before it. So things kind of split up. So, for instance, when j is 1, right? When j is 1, this says b sub 2 equals b sub 0 over 2. So it's 5/2. Great. When j is 2, you get this formula. Tells you, oh, and b sub 3 equals b sub 1 over 3. But b sub 1 was 0, so this is 0. When j is 3, you get b sub 4 equals b sub 2 over 4. So that is, okay, b sub 2. We had b sub 2 is 5/2, so we get 5/2 over 4. So you get 2 over 4. When j is 4, you get b sub 5. B sub 5 equals b sub 3 over 6, over 5. But b sub 3 was 0, so this is 0. What you should see is, at least for the even ones, when j is even, what's going to happen is you'll always get 0 because you're starting at 0, and if j is, okay, it's with j is even, it's if the subscript on the b is odd, so anyway, all the odd coefficients are going to be zeros, and that corresponds to the even j's here. But what's happening is if you're at one odd subscript, so let's say that j minus 1 is odd, then j plus 1 will be odd, and all the earlier odd ones are 0, so all the later odd ones will be 0. Every time you go up by 2, you get what you had before divided by j plus 1, but if this is 0, it's always going to be 0. So what we're concluding is that b sub k is 0 if k, all right, so the actual subscript on the b, not j, if k is odd. Okay, you're seeing this, and that's just because as soon as one odd one is 0, all the higher odd ones are 0 because this shifts by 2 each time in the index. Okay, so we can just concentrate on the even subscripts, so the odd j's. So let's just erase the zeros, and when j is 3, so let me rewrite the j equals 3 one. When j is 3, you get b4 equals 5 over 2 times 4. Yes, I know that's 8, but I'm waiting to see a particular pattern. When j is 5 in this formula, you would get b sub 6 equals b sub 4 over 6, so that it's 5 divided by 2 times 4 times 6. I'm going to do one more just to hopefully make the pattern blatantly obvious. When j is 7, you would get b sub 8 equals b sub 6 over 8. So you would get 5 divided by 2 times 4 times 6 times 8. What's the big deal here? You'll notice that this is just going up by, it's by multiples of 2, 2, 4, 6, 8. Well, if you factor out all those 2's, you can factor 2 out of each one of those. This is 2 to the 4th times 1 times 2 times 3 times 4. Right, I factored out 4 2's. Well, this was 5 over 2 cubed times 1 times 2 times 3. And in general, what you're getting down here, the numerator is always 5. The denominator is powers of 2. What power of 2? Half the index. And then you've got half the index factorial. So what I'm saying is, without proving it by induction, but just by seeing the pattern, you should see that if you have b sub 2k, so an even index on the b's, that what you're getting is that this is 5 divided by 2 to the k, right? K is half the index. 2 to the k times k factorial, this. All right. that tells us the whole series. It tells us all the coefficients in the series. We only get all the odd terms are 0, and the even coefficients are given by this. This is exactly what you get for this series. Now, it's whether you would see that if you didn't know it is another question. But we do know them. We do know it, so let's just quickly see that these agree. But, maybe before I do that, let me write out. We just found that this power series, we only get, right, it looked like this. But what we found is that all of the odd terms are 0. So this one's not here, this one's not here. And then the even ones go, oh, there's a 5, and then there's the 5 over, well, it's 2 squared times 2 factorial times x squared. And then there's a plus here, it's a 5 over 2 to the 4th times, did I just mess up? I did just mess up. Sorry, let's try that again. There's the B2 term, I looked at the B4 term, is 5 halves. The B4 term is 2 squared over 2 factorial. The b to the 6th term would be this, and so on. So you get this. Yeah, and if we had to, if we couldn't recognize this as something, you could just, kind of leave it like this and say, oh, and if I want to approximate the solution, maybe use these first 3 non-zero terms, which would mean go up to the x to the 4th term. But it is true that we know what this equals, and you can see it fairly easily. E to the x, we know that that's given by the series. The sum as k goes from 0 to infinity of x to the k over k factorial. So what is e to the x squared over 2? E to the x squared over 2, you replace the x there by x squared over 2. So you get the sum as k goes from 0 to infinity of x squared over 2 to the k over k factorial. But what is that? That is the sum as k goes from 0 to infinity of, all right, you get a divided by 2 to the k, so I'll write that in the denominator, 2 to the k, k factorial, and an x to the 2k. So you get this, which means that the coefficient, that's e to the x squared over 2. What does multiplying by 5 do? It just multiplies each term by 5. So you get this, which means that the coefficient in front of the x to the 2k term, so b sub 2k, is 5 divided by 2 to the k times k factorial, which is exactly what we found for our coefficient. So yes, it is exactly 5e to the x squared over 2. So this time, let's look at an example of a differential equation that's not separable. So you shouldn't have learned how to solve it in differential calculus. Maybe you did, but probably not. And let's see how a power series solution goes. I should say, however, that while this one is not separable, this is another one for which it's known how to solve this explicitly without power series. It's something called a first-order linear differential equation. But it's something you're not expected to know how to solve without power series, so let's do that. So let's take y prime equals x minus y, and y at 1 is minus 1. All right. And we want to find a power series solution to this initial value problem. Now our initial x value is 1, and so we want a power series centered at 1. So we will write, we want to look for a solution in the form, sum as k goes from 0 to infinity, of b sub k, but now times x minus 1 to the k. It's, because we're centering at 1, and go ahead and tell you that that x right there would look better centered at 1. And you might go, what does that mean? Center that x at 1. Well, you want to write it in powers of x minus 1. So I'll just go ahead and tell you that we're going to write that x as x minus 1 plus 1. So it too, this is the power series for x centered at 1. Right? Clearly, when you add these, you just get x, but it may not have occurred to you before, but this is the power series representation of x, but now centered at 1. And then so our differential equation will look like that. So you just do what we did in the last example. You calculate the derivative. So y prime is the summation starts at 1 because the constant term went away. You do the power rule. You get a k, b to the k times x minus 1 to the k minus 1. I will re-index this with j again, so I'll let j equal k minus 1, so that k is j plus 1. Okay, and then we find that y prime then is the sum, and now it's j. K starts at 1, so j starts at 1 minus 1. It starts at 0. K goes to infinity, so j goes to infinity. K is j plus 1. K is j plus 1. X minus 1 to the k minus 1 is j. This. And the other side, well, we don't really do much with the other side. It's just minus y. To have both indices with a j, I'm going to replace this k with a j, but you don't have to do that. It just makes things look a little more manageable, or I don't know, look a little more aesthetically pleasing. So the y prime that we get, the y prime you would always get, aside from possibly a different center, is this one. I just rewrote this, I hope. And then you get, so that's y prime. And then you get, let me write things, this has to equal, I'm going to write this kind of how I write series, so in increasing powers as you go to the right, this, and then minus this. So I'll write that as plus a negative. So I'm going to move the minus sign inside. But as I said, I'm going to write j's. J, x minus 1 to the j. We get this. And the coefficients in front of the various powers of x minus 1 on each side have to match, because two functions written as power series centered at the same place, there's the coefficients of the various powers have to match, the powers of x. But we have this little problem of these are kind of separate. They're not sitting, we can't just say, oh, j plus 1 times b sub j plus 1 equals minus b sub j, because we have these two extra ones hanging out. We can do that for high enough degrees, but we can't do it down here in degree 0 and degree 1, because so you have to split those off separately. So you want to look separately at the degree 0 and degree 1 terms. So when j is 0, over here, you're getting 1 times b sub 1, so you're getting b sub 1 for the coefficient, for the constant term here. When j is 0 over here, you get a minus b sub 0 as a constant term, but there's also a constant term right there. So you get a 1 minus b sub 0. So, right, let's check. It was constant term over here. When j is 0, you get a 1 b sub 1 times, we're just looking at the coefficient of the x minus 1 to the 0 term. 1 times b sub 1 equals constant term over here, 1 minus 1 plus negative b sub j. So yeah, negative b sub 0. We get this. When j, so we get this. When j is 1, you get what? So the degree 1 term over here is 2. So when j is 1, you get 2 b sub 2, 2 b sub 2. The degree 1 term over here, there's a 1 for the coefficient here, is 1 plus b sub 2, the j equals 1 thing over here, minus b sub 1. So minus b sub 1, that. All right? So that's what you get when j is 1. Aside from that, if you start at 2, this coefficient has to match that coefficient because these degree 0 and 1 terms don't matter anymore. And so we get these two conditions, and we get, if j is greater than or equal to 2, then j plus 1 times b sub j plus 1 has to equal that coefficient right there, minus b sub j. We never plugged in our initial data, and we should have, or it's not bad to do it at this point, but we have when x is 1, y is minus 1. That again gives you the constant term immediately, because what you get when you plug the center in is just the constant term. So this tells us that b naught is minus 1. Right? This says that b naught is minus 1. Because this series goes b naught plus b1 times x minus 1 plus b2 times x minus 2 squared, b2 times x minus 1 squared. When you plug in x is 1, all those are 0, and so b naught is minus 1. If you've centered at your initial x value, then b naught is always the corresponding y value. Okay, so where are we? We've got this. B naught is minus 1. B1 is 1 minus B naught. 2B2 is 1 minus B1. And we have this iterative equation right here that tells us how you get all the higher B sub j's from the lower ones. So in a harder problem, we'd essentially be finished right now. You would just have to leave it like this, but we can try to find, but we can look at the B's and see if there's a pattern that we recognize. And there will be, but that may not be obvious. So let me record where we are right now. We're looking for a solution of this form. And what we know now is that to have a solution of that form, we need b naught equals minus 1, b1 equals 1 minus b naught, b2 or 2b2 equals 1 minus b1, and then our big iterative formula for j greater than or equal to 2, that j plus 1, actually let me divide by j plus 1, b sub j plus 1 is minus b sub j divided by j plus 1. This. And we'd like to see what the b's are. And then if we can write it in a closed form, we will, and we'll be able to. But don't need to expect that. All right, B naught is minus 1. So B2, B1, this says B1 is 1 minus that, so 1 minus minus 1. So we get B naught is minus 1. B1 is 2. After that, let's see, we get 2B2. So we get B2 is 1 minus B1 over 2. B1 is 2, so we get minus a half. B1 is 1, so we get minus a half. We get that. And then we can start using our other iterative formula. Okay, how does our other iterative formula go? It's it tells us that B sub 3 is, actually let me check our work. It looks to me like I'm getting something that I shouldn't be getting. Oh no, it's fine. It's just, okay. We're just going to have to write things strangely to see that this equals the closed form that it equals. Okay. So when j is 2, what does our iterative formula tell us? It tells us B sub 3 is minus B sub 2 over 3. So it is minus a half divided by 3. So this is 1 over, and leave it as 2 times 3. You kind of expect factorials to pop up in a lot of series, so it's frequently a mistake if you're trying to see a pattern to multiply things out. So let's leave it like that. Then it says B sub 4. If you let j be 3, it tells you that B sub 4 is minus B sub 3 over 4. So this is minus, right, this divided by 4. So minus 2 times 3 times 4. And then B sub 5 would be minus B sub 4 over 5. So negative this divided by 5. It's a positive 1 times 2 times 3 times 4 times 5. Hopefully, you already see the pattern for j. In fact, even this one will fit into it. For j, right, it's minus, plus, so the sign is alternating. You do that with a minus 1 to the, actually let me go with k. You do that with a minus 1 to the k, or a minus 1 to the k plus 1. And then the denominator is the factorial of the b. So all you're getting is bk equals, well, it's a minus 1 to some power over the corresponding factorial, k factorial. We need, when k is even, we need to get a minus sign, so we need something that's odd up here when k is even. K minus 1 or k plus 1 will work. It doesn't matter. I'll pick k plus 1. So this is what we're getting for k greater than or equal to 2, which actually does work when k is 2. And then B0 and B1 are different. So what we're getting for our power series solution is this, that B0 is minus 1, B1 is 2, B for k greater than or equal to 2, bk equals minus 1 to the k plus 1 over k factorial. And so, and our series looks like this. Great. Well, if you want to write this in a closed form, you're going to have to look at it, mess with it for a while. But if you just wanted to approximate, you could just take the first few non-zero terms, or the first few terms. But if you really want to write out what's going on, it's so we're getting a minus 1 for b naught plus 2 times x minus 1 plus, and then you get then they start going according to this pattern. So a minus, so when k is 2, you get a minus. Maybe I'll write a plus there and a minus up here. A minus x minus 1 squared over 2 factorial, and then a plus x minus 1 cubed over 3 factorial, and a minus x minus 1 over 4 to 4 factorial, and so on. And you see this, and you see the powers of x minus 1 and the matching factorial, and you should think, aha, it's like e to the x, except instead of x, we have x minus 1. Yeah, that's true. In fact, if we put in an explicit, what about this alternating minus sign? Well, you know, that's a minus 1 to the, let me write it as a minus 1. I'll write this as a minus 1 to the 2 plus 1, or in other words, a minus times, maybe I'll not try to disguise this anymore. I'm going to write it, how do you make the sign alternate in a nice way? Well, I'm going to square a minus sign and keep this minus sign. That didn't change anything. I'm trying to make this match something we're familiar with. And the alternating sign, one way to see that you get it is to insert these explicit minus signs. So now something negative to an odd power, that's negative, but negative, so it's the plus that we had. What I'm saying is you should have all minus signs and think of this as minus x minus 1 to that power. And that will make the sign alternate. So minus, but then times a minus squared, it's still minus, but minus times a minus cubed, that's still a minus. Minus times a minus to the 4th, still a minus. The next one will be plus. What am I doing? This part, now we've got all minus signs. All of this part, it looks like, well, it's part of e raised to the negative x minus 1. Negative, right? So, right, if you, e to the x, its infinite series has the powers of x divided by the corresponding factorial added. But if you replace the x by negative x minus 1, then you get the quantity negative x minus 1 squared over 2 factorial. The quantity negative x minus 1 cubed over 3 factorial. You get that. We've got them all subtracted. So I've got this minus sign. But these terms aren't doing the right things. Right? This part we would have to write in a different way to make it match this pattern. This is the part of this series. This is the part of this series that starts at the degree 2 term. And if you make it match in the other 2 terms, we'll see a nice closed form for the answer. Not, keep saying this, not that you need to find a nice closed form for the answer in most problems. In most problems it would be too difficult to do. But it's not too difficult here. The other 2 terms that we would need to add, right, e to the x, looks like 1 plus x squared over 2 factorial plus x cubed over 3 factorial. If you replace this by minus x minus 1, then you replace all of the x's by minus x minus 1, so you get a minus x minus 1, minus x minus 1 minus x minus 1, okay, which looks like most of what we had over there, except I haven't inserted the minus sign yet. Minus, minus, plus, now minus, minus. So that part of the series that we have over there is this part. And so what we've actually got over there is minus, so that part that we were looking at was equal to minus e to the minus x minus 1, put this stuff over there, plus 1 minus x minus 1. So if you put that in over here, what you find is that our y is minus 1 plus 2 times x minus 1, and then you will add a 1, so plus 1 minus x minus 1, plus 1 minus x plus 1, and minus e to the minus x minus 1. So this is what we're getting for y. You can cancel these ones. 2 times x minus 1 minus x minus 1. You end up with x minus 1 minus e to the minus x minus 1. All right. We've done enough work now that you should verify. In fact, why don't we do this? Why don't we verify that this is actually a solution to our initial value problem? Y equals x minus 1 minus e to the minus x minus 1. This is what we just found, where we had to recognize what we had at one point as being part of is coming from the e to the x series by replacing x with minus x minus 1 and then negating. Should you be able to see that? Well, I don't know. Maybe. It's not too difficult, but recall what our original initial value problem was. It's kind of gotten lost at this point. It was y prime equals x minus y, and y at 1 equals minus 1. So is this really a solution to this? If we did everything right, it should be. I'm just saying we did a lot of little things, and you might want to check at this point. If you're sure you did everything right, there's no problem. Y at 1, when x is 1, you get 1 minus 1 minus e to the minus 0. That's 0, but then this is 1, so minus 1. Yes, we're getting minus 1. Good, good. Our solution satisfies the initial condition. Always good. And then y prime. All right, let me write it over here. If y is this, y prime is 1 minus 0 minus, and then the derivative of e to the something, you get the e to the something back. By the chain rule, you have to multiply times the derivative of the exponent, so we'll pick up an extra times minus 1, which will make, you can combine with that, and it'll make it a plus, 1 plus e to the negative x minus 1. And then we want to see that that equals x minus y. Well, what's x minus y is x minus 1 minus e to the minus x minus 1. The x's cancel, you get a minus minus, you get a plus 1, and you get a plus e to the negative x minus 1. Yippee! Those two things are the same, y prime and x minus y. So yes, this is a solution to the differential equation. It satisfies the initial condition, so it's a solution to the initial value problem. But if we had to leave it in infinite series form with our formula for the coefficients, we would have. Okay, I'd like to look at one last example of a second order differential equation, something we didn't look at in differential calculus much. Actually, we looked at 1 or 2, depending on how you count, when we looked at kind of infinite series for sine and cosine, or a fundamental differential equation that sine and cosine satisfy. Namely, that the second derivative is negative the thing you started with. So, and that's related to this example. I want to look at, as an example, y double prime equals minus 4y with no initial condition. So just this differential equation with no initial condition. This means that we don't have a particular center that's kind of handed to us where we need to center things. So I'm just going to pick the easiest one, x equals 0. We're going to look for a solution that's centered at 0. So we're going to assume that there's a solution that looks like this and find it. And then you can, in fact, verify it is a solution. But I'll say again, you can't really know it's unique. We'll know it's a unique power series solution. Although, with no initial conditions, they're going to be at least, you would expect for a second order differential equation, so with two derivatives, there'll be two unknown constants. So we're going to have two unknown coefficients, b0 and b1. But if you specify those or give enough data to determine those, then you'll know all the rest of them. So all of our coefficients will be expressed in terms of b0 and b1. So what do? Well, you take the second derivative. So that's easy. Y prime is the sum. You start at 1 again. The sum as k goes from 1 to infinity of k, b sub k, x to the k minus 1. Differentiate again, y double prime. Now you start at k equals 2. K equals 2 to infinity of k times k minus 1 times bk times x to the k minus 2. And now I'll re-index. I'll also, for aesthetic beauty, I'll call this index, I'll rewrite this in terms of j. We know this doesn't matter, but kind of it's nice to make them look the same. And now I'm going to re-index this. I'm going to let j be k minus 2. J is k minus 2, so k is j plus 2. This summation then becomes the sum as j. All right, when k is 2, j is 0. So this starts at 0. And as k goes to infinity, j certainly goes to infinity. K is now j plus 2. K minus 1, plus isn't showing up very well. K is j plus 2. K minus 1 would be j plus 1. And then k minus 2 is j, x to the j. So what are we getting in our differential equation? So we have no initial data. But we get that we're supposed to have y double prime equals minus 4y. And we just found that y double prime is this. And minus 4 times y, so it's minus 4 times our original series. I'll move the minus, but using j for the index now. Minus 4 bj x to the j. So the summations match. They both start at 0. They both have powers of x to the j. You just need, for all j, you need that coefficient to be that coefficient. So for all j greater than or equal to 0, we need j plus 2. Oh, I dropped a. Yes, there's a little problem back here. Good thing I noticed. Yeah, I had a b sub k here. You might wonder what happened to it over here. I certainly wonder. It should have been right here. This should have been a b sub k is j plus 2. So you get a j plus 2. Then the x to, got a little ahead of myself. B sub j. Yes, I should have noticed that when I rewrote it here. Let's try this again. Fortunately, the iterative formula looks so bad to me that, hey, where's my you get a b sub j plus 2x to the j. And this should equal the sum, as j goes from 0 to infinity, of minus 4 b sub j x to the j. So now let's try this again. You need this coefficient to be the same as this one. So for all j greater than or equal to 0, we need j plus 2 times j plus 1 times b sub j plus 2 to equal minus 4 b sub j. Or what's the same thing, dividing, assuming we've got the earlier ones and want the later ones, it's b sub j plus 2 is minus 4 bj divided by j plus 2 times j plus 1. All right, so this, and that's it. Now, we don't know b sub 0 and we don't know b sub 1, but what this tells us is that every time you know a coefficient, you know the coefficient 2 bigger than that. So that if we know b sub 0, we know b sub 2. If we know b sub 2, we know b sub 4. If we know b sub 4, we know b sub 6. At the same time, the odd ones. If you know b sub 1, you know b sub 3. If you know b sub 3, you know b sub 5. So the coefficients naturally break up into the even ones and the odd ones because the index, in our iterative formula, the index goes up by 2 each time. The index involved on the left and on the right. So what does this tell us that we get? So I'll write it again. B sub j plus 2 equals minus 4 times b sub j over j plus 2 times j plus 1. And I'd like to look at the even and odd coefficients separately. So b naught. We don't know b naught. Oh well, too bad. B naught is just b naught. Great. But then if you plug in j equals 0 here, you get b sub 2 equals minus 4 times b naught over, so we're plugging in j is 0, so over 2 times 1, so it's minus 2b naught. Okay. What's b sub 4? B sub 4 is what you get when you plug in j is 2. So you get minus 4. So we're plugging in j is 2. B sub 2 over, all right, you're plugging in j is 2 over 4 times 3. So you get this, and we had 1 times 2 and 3 times 4. So once again, you're starting to see factorials, which means, and at this point, you should realize, oh, it was probably a bad idea to divide that 2 into the 4. Let's leave it, if you're trying to see a pattern, let's leave it as minus 4b naught, and then divided by 2 times 1. Because now what happens, you get a minus 4 times b2. But b2 is this, so you get another minus 4. So we get a minus 4 squared times b naught divided by 2 times 1 times 4 times 3. So divided by 4 times 3 times 2 times 1. Okay. So let's do one more. B sub 6. That's when j is 4. Is minus 4 b sub 4 over 6 times 5. So you multiply this by another minus 4 and divide by 6 times 5. So you get a minus 4 cubed b naught over 6 factorial. Hopefully, at this point, you can see what's going on. We're getting that the even terms, so b sub 2n is, okay, it's a minus 4 to half of the index, so a minus 4 to the n times b naught over 2n factorial. Okay, that's what we're getting for the even coefficients. This is our formula. B sub 2n is minus 4 to the n times b naught over 2n factorial. If you want to write everything in terms of 2n, you can get a little tricky. You can write, and I am going to do this, but minus 4 to the n is certainly minus 1 to the n times 2 squared to the n. So it's minus 1 to the n times 2 to the 2n. And it is nice to write this that way. You get a minus 1 if you're trying to make it look like anything nice. So we get this, so that 2n up there matches the index on the b and matches the factorial. It's just nice to see that, yeah, the minus 1 still has an n on it, but hey, you can't fix everything. So that's what we're getting for the even coefficients. What about the odd ones? So again, we don't know. We don't know b sub 1. So b1 just happily sits there being b1. But then we have our iterative formula. That b sub j plus 2 is always minus 4 times b sub j over j plus 2 times j plus 1. And so we get something similar to what we just got. B sub 3 is, so that's when j is 1. It is minus 4 times b sub 1 over, so when j is 1, you get 3 times 2. B sub 5, that's when j is 3. You get it's minus 4 times b sub 3 over 5 times 4. Which means that if you put this in for b3, you get minus 4 squared times b sub 1 over 5 times 4 times 3 times 2. Do one more. B sub 7 is minus 4 times b sub 5 over 7 times 6. That means you pick up another power of minus 4, so you get a minus 4 cubed times b1, and then it's over 7 factorial. What are you getting? If you look at it, you'll see that what you're getting is the odd terms, b sub 2n plus 1. You're getting a 2n plus 1 factorial. You're getting a b sub 1, and then you're getting minus 4. Minus 4 to the, you subtract 1 from this and divide by 2. So, right, it's, if you have 7, you subtract 1, you get 6. This is 3. If you have 5, you subtract 1 and divide by 2, you get 2. In other words, when the index is written like this, it's just n again. Right? So, for instance, when n is 3, b sub 7, you get minus 4 cubed. Right. So we're getting this. And once again, it's nice to rewrite minus 4 to the n. Minus 4 to the n is minus 1. Minus 1 to the n. And then you've got let me do this. All right, it's a minus 1 to the n times a 4 to the n. That's true, which is 2 to the 2n. But we would like for this to be kind of 2n here, and we'd like a 2n plus 1 just to match this factorial in the index here. Well, you could do that as long as you put a half out in front. Now, it's not clear that you should know that this will give you something good, and maybe it doesn't necessarily give you anything good. But let's write this as a plus 1, which means we just multiplied times an extra 2. You can't just do that without compensating for it somewhere, so I'm going to write a half times this. I didn't change anything. It's still, this is minus 4 to the n, but you get that. Okay. So this is what we get for our even and odd terms. It's a completely separate question of whether you can recognize this. as anything particularly nice. You can write it in terms of sine and cosine, because what we're getting, assuming we're allowed to split up the even and odd terms, which there's a theorem that tells us that we can, we have a series that looks like this. But what we've just said is that, or what we've just found, is that it looks nicest to split this up into even and odd terms and do this thing. So take the even terms, starting at 0, and add to that the odd terms. Starting at n equals 0, make the start at b1, and separate it like that. If you do this, what you find is, this is the sum as n goes from 0 to infinity, of b sub 2n, which is minus 1 to the n, 2 to the 2n, b naught, over 2n factorial times x to the 2n. And this part is, we have this, is the sum as n goes from 0 to infinity of b to the 2n plus 1, or b sub 2n plus 1. So minus 1 to the, I forgot the half. There's this half sitting out in front, times minus 1 to the n, times 2 to the 2n plus 1, times b sub 1, divided by 2n plus 1 factorial times x to the 2n plus 1. Now, this may not look like anything you're familiar with, but let me try to make it look better. So you can, this is what we get, but factor out the b naught. So we factored out this b naught. Here's 2 to the 2n and x to the 2n, right? That is 2x to the 2n. Add to this, we can factor out the b1 and the half, so we get a b1 over 2. And here you've got 2 to the n, that should have been, I didn't write that correctly, that should have been a 2 to the 2n plus 1, because I want to merge it with that, so that's what that should have been. 2 to the 2n plus 1 times x to the 2n plus 1, you get a 2x to the 2n plus 1. And hopefully, this looks better to you. This should look familiar, and I'm now double checking to make sure I have gotten the right answer. Yes. This is cosine. This is the series for cosine, not of x, but of 2x. This is the series for sine, but not of x, but for 2x. So once again, after telling you many times that you shouldn't expect nice closed forms for the solutions, I have given you ones where you can, if you had to, do this. This is cosine of 2x, and this is b1 over 2 times the sine of 2x. And yeah, initial data would determine b0 and b1 for you. But without it, this is just the general solution where b0 and b1 are unknown constants. Anyway, these are examples of how you find power series solutions to differential equations. You write that you've got some power series centered, well, either at the x-coordinate where you're given initial data, or at 0, or someplace convenient, or that you think is going to be useful later. You take derivatives, multiply, do whatever addition and subtraction you're required to do whatever the differential equation tells you to do. You get two power series that are equal. You want to reindex so that it's easy to match the corresponding powers of x on both sides. And then the coefficients in front of the various powers of x, or x minus a, on both sides have to match. And this gives you iterative equations, so iterative formulas for the different coefficients. And sometimes if you look at the pattern, and you write things the right way, you'll see what the pattern is, and you can write a general formula for each coefficient, for the BKs. In other problems, you might not see a pattern, or there might not be a nice recognizable pattern there to be seen. And then you would just find the first few coefficients and use the partial sum that you get, so the Taylor polynomial that you get, as an approximation that works well near the center. We're going to start a new chapter of the book next, and the next chapter will deal with sequences and series of constants. In a way, what we're about to do is all the technical details that you need to make all the stuff we've talked about in power series actually work. So that's what we'll do next.